Hello, thanks for joining us on Space Nuts, the podcast all about astronomy and space science, also heard on community radio across Australia. Thank you for joining us. We've got a lot to talk about today, including methane, which might be a good marker for perhaps life on exoplanets. The speed of sound on Mars, which apparently is quite slow. They do sort of fall behind over there. And we've got audience questions about whether or not the sun has seasons, why the moons and rings of Uranus are also rotating on a tilted plane, and how do you get into astronomy? How do you make it your career? Somebody wants to know because they're sick of digging holes. We'll explain all of that on this edition of Space Nuts. Thank you for joining us.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Great to be with you once again on episode 298, no less, and getting very close to episode 300. And since we spoke to you last, our plans have not actually gone another inch forward, but we're working on it. Well, we're not, but we have. We have ideas. I'm Andrew Dunkley, the host, and joining me, as he does every week without fail and under great duress sometimes, is Professor Fred Watson, astronomer-at-large. Hello, Fred.
Good. Well, it's morning, afternoon, or evening, depending on what time you're listening. Andrew, how are you doing?
Now, Fred, I'm well. I'm quite well, despite being surrounded by people with COVID at the moment. Everywhere that I work, everyone's either had it or got it at the moment, and I haven't. And I'm wondering if I've actually caught it and just been one of these lucky people who had zero symptoms or next to no symptoms. I don't know. I'm still playing it safe, but you've not been so lucky. You're stuck down in Tasmania in the great city of Launceston.
That's correct, yeah. So I can't remember whether we mentioned it, but Marnie, my partner who runs tours, which is one of the things we've done for 15 years together, taken them all over the world. We had a tour down to the islands of Tasmania. So Tasmania itself, then Island, King Island, and finally Flinders Island, which is quite a remote area, population 700 or something like that, 900
I was
maybe.
going to say 7. I wasn't far off.
Far off, yeah. To the north of Tasmania. And that's where we wound up at the end of our tour, the final day of our tour. A certain Fred Watson tested positive for COVID, followed by most of the rest of the group. And so yesterday we were, thanks to negotiations by Marnie, I have to say, I don't know how she did this. She made 200 phone calls yesterday. She basically pulled us out of there on a medevac flight. We had our own chartered aircraft with a crew who were suited up with PPE to take us elsewhere because the medical facilities on Flinders Island are not such as could cope with a large influx of sick people. So we wound up in hotel quarantine here in Launceston, which is where we're going to be for at least the next week. Unable to go out. Fortunately, it's a lovely spot. We've got a beautiful view of the river out the window there. I hope all our colleagues are as lucky. The interesting part about it all, though, was just how everything swings into action. So Tasmania Health were really good in the way that they cottoned on to the fact that this was, it was quite an important thing that we needed to get these people off the island and everything else. And I should give a shout out as well to Darren at Lady Barron, which is one of the towns on Flinders Island. He was our host in the lodge we were staying in. He did a brilliant job to cope with all these folk who are not very well.
Yeah. I think you're the first person I've actually spoken to while they've had it.
Oh, well, yeah, okay. So this is what it looks like, Andrew.
You look the same, but obviously it's all, up here and down there. It feels
that's
different.
Right. Yeah, all of us have gone through a period of feeling as though you've got a really heavy dose of flu and not feeling very well at all. But that sort of lasted 2 or 3 days, and generally speaking, I feel pretty well today. I get the sweats and things like that occasionally, but hopefully. So I tested positive on the 27th, which is where are we now? It's 3 days ago, I think. So we'll see how we go. We're all going to get tested again today, apparently.
Yeah.
Hopefully
Well,
not in the middle of...
Just move a bit further away if you don't mind.
I'll breathe.
Launceston's not far enough.
I'll breathe away from the screen. How's that?
Yeah. Oh, gosh. Well, now, fingers crossed that you're on the mend. I've heard stories about how it hits you hard early and then you just sort of work your way out of it. And, after a week or so, you go, well, what was that all about?
Yeah.
But sometimes it lingers. You just don't know. It's different for everybody.
The dreaded long COVID, that's something I'd rather not have. Yes.
Yeah.
But anyway, so far so good.
Yes, indeed. Well, thanks for doing this under the circumstances. I mean,
that's fine.
I suppose it breaks the boredom a bit.
There's no sign. I think I was last bored in 1959, Andrew. So there's always so much going on.
Yes, that's very true, indeed. And there's certainly a lot going on in the universe when it comes to exoplanets. When we dovetail this into our first story, they're suggesting that methane might be a good biomarker when searching for life. That shouldn't come as a surprise, I suppose. But it's now been sort of put forward as the biomarker, perhaps.
Potentially, that's right. Yeah, it's a really interesting story, and it does go back to things that you and I have spoken about before, because methane is a well-known biomarker. Most of the methane in the Earth's atmosphere is produced biologically. And we've got this intriguing thing that we keep spotting plumes of methane on the planet Mars, which we've had great trouble tying down. And there's something going on there that we don't really know. It could be residual volcanism, because that's the thing about methane. It's not just a compound that is only produced by life. It's got other sources as well. Volcanism is one. Actually, you would get it from colliding, from meteorites or something like that, or an asteroid impact would generate methane in an atmosphere. So it's certainly of interest to astrobiologists, but isn't clear cut until now, because this study, which we're reporting on, comes from scientists at the University of California, Santa Cruz. And what they've done is they've, first of all, taken another look at methane as what we call a biomarker, something that would reveal living organisms in an atmosphere, and compared it with one of the other principal biosignatures, which, of course, is oxygen, because oxygen largely is generated by living organisms. If you found oxygen out of balance with other chemicals in the atmosphere of a planet, as it is on Earth, it's out of balance chemically, and it's the life that keeps it there, then that's a really good biosignature. But what they've done is, and this is it's a great thing to do exactly at this time, they've looked at this in the context of observations with the James Webb Space Telescope. Excuse me. And in fact, oxygen is not easy to detect with the James Webb Space Telescope, whereas methane is. And so what they've done in this study is looked at, if we detect methane, what can we also look for that would tell us that its origin is biological rather than something else? So they've developed what they call a framework for, interpreting the observations. And so, in fact, there's a signature from, there is a quote here from Maggie Thompson, who's actually a graduate student at UC Santa Cruz. She says, we wanted to provide a framework for interpreting observations. So if we see a rocky planet with methane, we know what other observations are needed for it to be a persuasive biosignature. And what they've done is they've said, okay, what are the non-biological sources of methane? And they include volcanoes. They include, places like mid-ocean ridges, which we've got running down the whole Atlantic Ocean. They release methane too. hydrothermal vents, which you often find along those places, all the big picture stuff, tectonic subduction zones, the stuff that's going on in the surface of the Earth, which may be going on in the surface of other planets. We don't know whether other planets or the planets of other stars have plate tectonics, but you can bet your life if we do, they probably do as well.
Yep.
And
yep,
so
they would.
So what they've done is, looked at what you might find alongside methane that would tell you that the methane was more likely to be coming from a non-biological source. And one of the clues is, if you find a large amount of methane, then there's a really good chance it's biological, because most of these other things that we've just mentioned, like volcanoes and tectonic plates, they don't emit as much methane without carbon monoxide. So you've got to look for the other elements as well, because biological activity consumes carbon monoxide, and that and produces methane. So that would be the kind of thing you'd be looking for, the ratio of, for example, methane to carbon monoxide or carbon dioxide and other chemicals as well. So it's a really neat set of frameworks that they've provided, almost like a recipe for, for what a life-containing planet might do in terms of the shape of its atmosphere.
Okay, so are we suggesting perhaps that it's feasible for the James Webb Telescope? That's all right. Is it feasible for the James Webb Telescope to focus on an exoplanet, for example, and go, okay, this is a prime candidate for life because we've found all this in the right proportions?
Yes, exactly that. One of the things that we talk about when you're looking for life on other planets is non-equilibrium chemistry, and that's what I was just talking about. If you've got oxygen there in large quantities, then it's out of equilibrium chemically. Yeah. So I think this is a really good paper, which I think kind of sets the scene for future work with James Webb Space Telescope.
If you'd like to read that paper, you can see the report on this fabulous website that we both very much love. phys.org is where you'll find that story, because I think it's great. You know what else it would tell us, Fred, if we found the right formula? That there would obviously be a lot of cattle on this particular planet, and therefore probably McDonald's.
There's an inference. I wasn't going that far. I thought you were just going to do the cattle, but and there's a widely held misconception about which end of a cow the methane comes out of.
Is that right?
Yes, which we discussed in detail on our tour around the islands of King Island. Of course, is full of cattle, because that's where we get all this wonderful dairy cheese. It's the front end. That's where the methane comes from, not the other end.
Right. I didn't actually know that. No. So obviously fell for the half-truths as well.
Yeah, we all do, yeah.
So, King Island cattle. Guess what's on Kangaroo Island?
Oh, I don't know. Well, that's a really good... Would it be ducks?
There'd be probably ducks there too. But it was so named because I think it was Matthew Flinders that found good resources on Kangaroo Island and food for his sailors. And is it that one or one of the other islands, maybe a few islands around that Tasmanian chain, that have some of the biggest venomous snakes in the world?
Yeah, we saw one too.
Oh, did you? Yeah, they're enormous.
Yeah.
Because of their isolation, they grow bigger for some reason. So they're on the right track with King Kong. It's actually true that
King Island
animals
Kong,
living in isolation grow much, much bigger. Yeah.
Yes.
All right. So keep an eye on future developments with the James Webb Space Telescope and those exoplanets and the possible methane marker. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying was a go.
Space Nuts.
Now, if you haven't visited our website recently, pop along and have a look. We're adding to it all the time. There are several stories a day that get published on the Astronomy Daily tab. You can visit the shop and get Fred's latest book, which is going gangbusters. I think Marnie's bought 3 or 4 copies for him now. And there's there's all sorts of other things to do. And it's, of course, where you can send us your questions, which we'll get to later. If you are listening on the podcast, we do the questions mainly then. Now, Fred, we're going to talk about the speed of sound. Now, I've done a bit of homework here, and at sea level, the speed of sound on Earth is 344 metres per second. But we're going to talk about the speed of sound on Mars because it's different, and it's different depending on the circumstances on Mars.
That's right. I always have 330 metres per second in my head for the speed of sound, but it might not be at sea level or something like that. That might be the wrong pressure.
Well, it depends. It says here it's 344 metres per second at 21 degrees Celsius under normal atmospheric conditions.
Yeah, that sounds about right. But basically it means... so that's a kilometre every 3 seconds, which is it ties in with remember you count to 4 after you've heard of every 4 seconds is a mile away for a thunderclap following a flash of lightning, and that sort of ties in with the same thing. So roughly 340 meters per second on Earth, but on Mars. As you've said, the speed is different. And you wouldn't expect anything else, really, given that the atmospheric pressure on Mars is, 0.6% of what we have here on Earth at sea level. So the air is very, very thin. It's not too thin to have quite strong winds, though, and that's certainly one of the things that has been experienced by the various Mars rovers. But anyway, how do you measure the speed of sound? Well, you listen closely. Yeah, I mean, in fact, Perseverance, the rover that's done this, is well equipped to do it because it carries microphones, and I think it's the first of the NASA rovers that has actually had microphones on board. And you and I have played the sounds of Mars before on the show, played some of the recordings from the microphones. I think we once played the drone of the Ingenuity helicopter as well as it was flying. So what they've done is the NASA scientists have looked for something that they can identify as being the source of a sound, and measure how long it takes for that sound to get to the microphone, because they know where the microphone is, and if they know that where the source of the sound is, then you've got the speed of sound. And in fact, what they've done, I thought, when I thought about this, I thought, oh, well, perhaps they'll do something like, kickstart the Ingenuity helicopter's rotors, because that's several meters usually from the rover. And if you know when the rotors kickstart and you know how far away it is, and then you pick up the sound of that happening, that might give you a measure of the speed of sound. But I guess that might just be too not specific enough a sound to do it. So they've chosen something nearer, and it's probably not that near. I think it's probably up to 3 meters away or something like this. Perseverance, like Curiosity, has a laser zapper, to give it its technical term, which basically zaps rocks, and they look for the plume of vapor that comes off it when you vaporize a little bit of a nearby rock. And so what they've done is they've zapped a rock, and they know when that instant takes place. And of course, the laser over that kind of distance, a beam is essentially traveling at infinite speed. So that pinpoints the sound, the event itself, and then what they can do is time the delay till that little click from that zap is heard by the microphone. And when they do that, they calculate that sound is traveling at about 240 meters per second, sort of 2/3 of what we have here on planet Earth.
Yeah, that's fascinating.
I think so too. But what's more surprising, because this doesn't really happen on Earth, it's that if you go to higher frequencies, you get higher speeds. So,
Wow.
in fact, the figure that's being quoted in the article that I've been reading says the speed increases by approximately 10 meters per second above 400 hertz. So that's, 400 hertz is not far off, the A on a piano that you tune to. It's A above middle C. But what that means is if you've got different frequencies coming at different speeds, assuming that you could talk to people on Mars, and of course you can't because the atmosphere is far too thin, but you can imagine that the different frequencies in your voice would arrive at different times.
Oh, gosh, can you imagine that?
I mean, it's bad enough, trying to understand what people are saying when that doesn't happen. But yeah, can you imagine it? That would be pretty garbled. But
yeah, I've sort of made a joke of it in the past, but because of the thin atmosphere, hearing someone talk, if you could talk openly on the surface of Mars, would be really muffled, apparently. Very, very difficult to literally pick up what the words are because of the muffling effect. But if you've also got the different frequencies arriving at different times, that could be a nightmare.
Yeah. It would. Tell you what, it would make Space Nuts sound good, wouldn't it?
Yes. Well, we talk like that anyway. The best
We're
of times.
all on different frequencies. Yeah, but really interesting finding. And so it kind of sent me looking, to what happens on Earth. And generally speaking, on Earth, the frequencies arrive more or less at the same time. And it's obviously to do with the physical structure of the atmosphere, the properties of the atmosphere itself. And maybe that thinness of the Mars atmosphere is what actually causes that separation of frequencies.
Maybe. And it opens up the question as to how sound goes on other planets.
Yeah, that's right.
What it might be like if you could stand on Venus, for example, or Pluto. It just proves that we are certainly endemic to this planet and not built to be anywhere else.
That's quite correct, Andrew.
We would have a lot of trouble.
Yeah, we might wind up talking about this again, though, because the little team that's working on this is they're going to continue this work, monitoring and analysing sounds from Mars to see how the effects change during the Martian seasons, because temperature changes on Mars over seasonally, and of course they get these dust storms as well on Mars. So it'd be really interesting to know what a dust storm does to the way sound is transmitted.
Yes, of course the solution to this we already have, and that's wireless.
Yes, that's a good idea. Why didn't I think of that?
So even if you could walk around without a spacesuit on Mars, even if the atmosphere made it impossible for you to talk to each other, you could do this. You could microphone and headphones, all solved.
Solved. What a great idea.
It worked for Apollo, didn't it, on the moon?
Well,
they could talk to each other.
Of course they did, yeah. So,
we already have the solution to the problem, but it is really interesting to be able to... And who knows what we could learn from that kind of situation.
Well, it's telling us about, the properties of a very different atmosphere from what our Earth's atmosphere is. Yeah. A nice piece of work, nicely done to think about measuring the speed of sound on Mars.
Absolutely, yes. All right. This is Space Nuts. I'm Andrew Dunkley with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Now, I'd like to say thank you to everyone who's sent in reviews for Space Nuts, because it's been fantastic, the response. We've had, I think, on one particular platform, over 250 reviews, maybe more, I don't know. And I'm so pleased to see that our star rating is half a star, short of 5. Gotcha. Short of 5, 4.5 stars. So thank you for the positive reviews. That's greatly appreciated. And the more reviews, the better. it spreads us out to more and more potential listeners who have an interest in astronomy and space science, and we'd really love to get hold of them and just sort of grow our family. So if you want to do some reviews on your podcast distributor for us, that would be most appreciated. So thank you to everyone who's done that so far. Now, Fred, we've got some questions to deal with. This first one comes from Josh. Is it Josh? No, it's from Josh. Yeah, it is from Josh. There's two Joshes. Okay, that's what confused me. So Josh said, just want to congratulate you both on the incredible podcast. I came across it late last year. I'm still catching up on all the episodes. I do have a question about the sun, if it hasn't already been answered. Does the sun have seasons or weather cycles like we have on Earth or on other planets? If so, how does changing condition on the sun affect Earth's weather? I guess we've touched on it from time to time, but it's worth discussing again. Does the sun have seasons?
Indeed, it does. Dramatic ones too, Andrew, as you say, we have talked about before. But they're different. Of course, the seasons on Earth occur because the Earth's axis is tilted over at 23.5 degrees, which means that, for part of the year, it's the northern hemisphere that gets the most sunlight. For part of the rest of the year, it's the southern hemisphere that gets the most sunlight. And
yes, we're in that transition right now, aren't we? We're certainly noticing cooler conditions here at the moment.
Yeah, as we transit from one to the other. But the sun, and I guess the sun's implicated in that it's the sun's radiation that we're receiving on Earth that gives rise to, well, first of all, our environment, but also the seasons that we experience throughout the year. Whereas the sun itself has its own kind of internal seasons, and they've been known for a long time, probably a couple of hundred years, maybe even longer. When people first started, actually, it's definitely longer. That's probably more like 300 years. When people started counting the spots on the sun and realized that these sunspots, the numbers fluctuate seasonally over an 11-year cycle, which we call the solar cycle. So just thinking about it, I think we're now on cycle 26. So, you're talking about the best part of 300 years that these have been observed for. I don't know who it was. It's probably Maundra or somebody like that who kicked in number one. Anyway, never mind. The fact is that the easiest thing to observe on the sun is the change in the sunspot cycle over long periods. As I said, 11 years. So they go up to a maximum, which also coincides with things like more geomagnetic storms, with heightened visibility of the aurora borealis and aurora australis, because of the stream of particles that comes from the sun. That thing that we call solar wind gets a bit stronger during these times, and sometimes you get solar storms, which can actually cause power blackouts and things of that sort. Yeah. So those are all phenomena that have been well known in terms of, just observing what actually happens. But it's only really within the last 20 years that we've had any clue at all as to what's really going on the sun. We've known for many years, probably best part of a century and a half, that sunspots are magnetized, that they usually come in pairs, sort of side by side, and the two pairs have opposite magnetic polarity, so one will be north and one will be south, and that switches between solar cycles. So, if you've got northern hemisphere sunspots with North Pole leading as the sun rotates, in the next solar cycle it'll be the South Pole that's leading in say the northern hemisphere. So do they know why that happens? Well, that's the thing. No, until recently, nobody had a clue. They knew that magnetism played a part in it, but now we've got several really competent spacecraft observing the sun, festooned with instruments, including one that actually skims the sun's outer atmosphere, the Parker Solar Probe, and so the magnetism is now sort of mapped in much more detail, and the understanding is there are processes going on beneath the sun's surface. And of course, the sun's a ball of gas, so it doesn't have a solid surface that you could ever stand on. But we've got what we define as the surface is that point beyond which you can't see. All you can see is a brilliant shining thing, which we call the photosphere. Beneath the photosphere, there's this, what's usually called a conveyor belt of like circulating material, which is stuff going, if I remember rightly, it's going up from the equator to the poles and then circulating lower down in the sun's atmosphere, circulating back again. This gigantic conveyor belt that's carrying the magnetism and sunspots too, so that you've got this really extraordinary almost a magnetic dynamo, if I can put it that way, that's taking place inside the sun, giving it these well-defined seasons. It is really remarkable what we've learned about the sun over the last 20 years or so. And I'm not a solar physicist by any means, so I'm not really explaining it very well. But there is such interest there, and Josh might want to check out on Wikipedia, have a look at things like the solar conveyor belt. And yes, there are seasons on the sun, and they're very, very, very robust. The 11-year cycle has been known for, as I said, probably 300 years or thereabouts.
Yeah. And then we experience change on Earth during those cycles too, don't we?
Well, that's right. Sorry, yes, that's the other part of Josh's question. Yes, there are interesting mechanisms that are not well understood. So in the late 17th and early 18th centuries, there was a period when there were virtually no sunspots on the sun. It's usually called the Maunder minimum because of a very famous husband and wife astronomy team, Annie and Walter, I think it was Maunder, who noticed these things and wrote about them. So the Maunder minimum was there were no sunspots, but it also coincided with a kind of mini ice age in the northern hemisphere. Probably not down here. It was probably the northern hemisphere. And it's thought to have been caused by the fact that the sun is quiet, so you get fewer subatomic particles coming from the sun. But what that does is it lets in other subatomic particles that come from the universe, what we call cosmic rays, high-energy cosmic rays. And they are thought to have disturbed the northern hemisphere jet stream and disturb it in a way that the jet stream doesn't allow warm air to come up and sort of thaw out the winters. That basically you got this, as I said, it was 70-year ice age, effectively, mini ice age.
Fascinating. Yeah.
So there's clearly a connection. It's not properly understood, but we do believe that there are connections between the seasons on the sun and the Earth and the behaviour of the Earth.
There you go, Josh. Great question. Thanks for asking that one. Let's move on to a question from Judd. I think we've heard from Judd before in the past. And he wants to talk about Uranus. I'll sort of paraphrase this just to keep it short. But he says, Brian Cox mentioned how Uranus spins on its side. And, of course, you did so in your book, which Judd says he hasn't read yet. So the answer might be in your book. Why is Uranus upside down? Its axis is tilted over, possibly due to a collision with a planet-sized object. He says that would have been something to see. Yes, you wouldn't want to be too close. Computer simulations suggest that when the planet was knocked on its side, all its moons and rings followed it and then rotate along the same tilted plane, which prompts him to wonder why. They're not physically connected to the planet. It's just a sphere of mass. So how would the moons and rings orbit be altered by the tilt of the planet's axis? That is a good question, but it's probably self-evident. Would not most rings and moons follow the axis of the rotation?
Look, I get the question. I think it is it's an important one, and it's because there isn't a physical connection as such. It's not bits of string that they're on. You can imagine
it's gravity, isn't it?
Yes, so it's gravity. And so gravity is doing the job. And in that regard, you might expect exactly what you've described to happen. But you can also think of a situation where you've got Uranus on its side and moons and rings are orbiting in different planes. So I think what we're saying is that it's basically exactly as you've outlined, Andrew. I'm trying to be a devil's advocate here, but you've already got the answer. It's the gravitational grip that Uranus has on these objects that take, that take them around its equator, rather than, even though the equator's tilted on its side, that's, tilted, so the pole's tilted on its side, so the equator's almost vertical, and give it this curious effect. What to me is more difficult to envisage is when that collision occurred. That is possible that's when some of those moons were actually created, because there would have been debris, and you've only to think of the origins, as we understand them, of the Earth's moon, which came from a collision by an object we call Theia, about the size of Mars, when the Earth was barely in its infancy. So there's a collision with the Earth, the proto-Earth. It lifts debris up and forms the moon in its present orbit. Sorry, my computer's slipping off my improvised stand here. It's going to fall in my lap in a minute. So I think you're right. It's the collision itself may well have caused some of that debris, and by that include the moons as well as the computer's got a life of its own here. Just hang on a bit. How's that? There we go. That's better.
That's got it.
Yeah. The moons would naturally follow the rotation of the planet. That's a terribly garbled explanation, for which
that's all right.
For which I apologise, John. But yeah, your statement, they're not physically connected to the planet. As Andrew has said, they are physically connected. It's gravity that is the force that does that.
Yeah. And Judd, there is the book. If you want to grab hold of it, you can get it through the Space Nuts shop, and page 153.
Okay.
There you go.
I wish I'd read that.
As to why Uranus is upside down, but it's not. It's not quite upside down.
No,
but,
it's on its side, yeah.
Yeah, it's certainly very sleepy giant, that one. Now, thanks, Judd. We'll go to our final question, which comes from another Josh. Now, Josh actually comes from a town that's just down the road from here, in Dunny, the name of the town. Stop laughing, you Americans. Dunny, well, you wouldn't know, but Dunny is a colloquial name for a toilet in Australia. So Dunny cops a bit of a ribbing. They were actually going to put a big Dunny there once, but it got voted out, which is probably a good thing. But anyway, Josh is from Dunny, but he's a miner in the Hunter Valley, but he's been saving his money for a career change. And he's telling us, Fred, that he wants to give up the 13-hour night shifts to switch to another night occupation, that of astronomy. He wants to know how he could get into the trade. What do you think?
Look, it's a great aspiration, and there is already a person who has done exactly what Josh has in mind. Only he was made redundant, but he was a miner in Broken Hill. I don't think he'll mind me giving his name, Trevor Barry. He's very, very distinguished astronomer now, because what he did with his redundancy money was he set himself up with his own private observatory, but made a speciality of observing the planets, the giant planets, and in particular Saturn. You and I have talked about Trevor before, Andrew. His observations of Saturn were used to steer the Cassini spacecraft to examining, the features in Saturn's atmosphere that were of interest. So he was almost like the scout, had his observing Saturn every night, so he knew where all the storms were cropping up. Really interesting was going on in the atmosphere. He could get in touch with his colleagues at NASA, and they pointed the telescopes on the Cassini spacecraft in the right direction, and it's produced a huge number of scientific papers. And Trevor is just such an inspiration for somebody whose career as a minor, and now is an author on papers that that get published in the top journals because of the work that he's done. So there's somebody to inspire you, Josh. What I'd suggest is to kind of follow the path that Trevor took, and it needn't necessarily involve buying your own telescope and making your own observatory and doing the kind of work that he did. But what Trevor did was took an online course, and there are several, an online astronomy course. He did one of the ones at Swinburne. So it was something like a graduate certificate, I think, that he got in astronomy. There are now others. The University of Southern Queensland does fantastic work in this area, and I'm not just mentioning that because I've got an honorary professorship there, but they do. They're great at this broad education. And they also have, at University of Southern Queensland, they have facilities. There is an observatory, Mount Kent it's called, not far from Toowoomba, up there in Southern Queensland, where they do really interesting work on exoplanets and things of that sort, which rely on their students and their supporters to operate. I think a lot of it's done robotically, but I would have a look at the online courses. Swinburne certainly is a possibility, and they still do fantastic ones. But check out University of Southern Queensland and Mount Kent Observatory to see whether you could do one of their courses, or perhaps involve yourself with the work that they do, because the more people involved in this, the easier it becomes. Just going back to your comment about Dunny Andrew, there is a segue that we could have made from the previous comment, because
of course,
Dunny when back in 2006 we put together the world's largest solar system model, Dunny was very keen to have Uranus there.
Yes,
because it sort of fitted in somehow. But in fact, it doesn't fit the geometry of this. Most of our listeners won't know what this is. The world's largest virtual solar system tour.
And basically, all roads leading into all major roads leading into Coonabarabran, where your observatory is, were lined with the planets of our solar system on a scale that put them at the right distance from Coonabarabran, the observatory, which was the sun.
Yeah, 1 to 38. And 1 to 30 million is the scale.
Yes, and so here in Dubbo, we are near. Is it Pluto?
You've got Pluto, yeah. Because Pluto was included because it was just being reclassified when this all happened, and in fact we had to change the captions on the Pluto boards. But yeah, it's scaled to the diameter of the dome, which is like half a sun. That scale to the size of the sun gives you 1 to 38 million, and the planets are lined out on the right length. Unfortunately for Dunny, what you get there is Neptune and not Uranus. So I think they've got Neptune.
Would have been the perfect combination.
Would have worked, wouldn't it?
Yeah. Anyway, Josh, good luck with your studies, and hopefully we will be talking about you in the not too distant future.
That would be great, wouldn't it?
Making some magnificent discoveries in astronomy. And thanks for your questions. And if you do have questions for us, don't forget to jump on our website and send them to us in text or voice form. Everything you need to know there. The AMA tab is where you can go to record your voice or send us text, or the little tab on the right-hand side, send us your questions or whatever it is that says is another way. As long as you've got a device with a microphone, such as a smartphone or a tablet or a laptop or something, you can send us questions. And, that's the way to do it. spacenutspodcast.com or spacenuts.io is where you can go to see the website and check out the shop and send us your questions, or just send us some information, and don't forget to do some reviews for us as well through your favourite podcast platform. That brings us to the end, Fred. Oh, by the way, you were wondering about your fellow travellers down there in Tasmania who were on your tour group. You are, of course, staying at the 5-star Royal Hyatt Hilton in Launceston. They tell me that they're at the Diamond Dollar Motel at downtown. So You got the better deal.
I won't buy into that one because he's a bit sensitive at the moment.
I'm sure. I just can't help having a bit of fun with you. But listen, under the circumstances, thank you. I know it's been a tough haul these last few days, but Godspeed, and both you and Marnie and the rest of the tour group get well soon.
Yeah, I think we're on the path to recovery. Hope so anyway, and we'll find out next week.
Yes, we will. And we'll talk to you then, Fred. Thank you so much.
No worries. See you later, Andrew.
Okay. Fred Watson, astronomer-at-large, part of the team here at Space Nuts. Of course, Hugh back in the studio, twiddling his thumbs and wondering what to do next. Thank you to you too. Now, next week is 299. We hopefully will tell you then what to do to listen live for episode 300. That's still the plan. So we're going to work out our times and try and translate that into we might do it in Zulu time so that everyone knows what time we'll be on. I don't know yet. But we'll figure that out and tell you next week. But for now, thanks for joining us on another edition of Space Nuts. From me, Andrew Dunkley. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.